Okay, welcome to the latest talk on science and religion. And today we're going to be looking at truth. Specifically, we're going to be looking at truths that you can see and truths that you cannot. So this is a diagram that you're all well acquainted with right now. We've been circling around it for the last couple of weeks. So we've looked at objectivity and objective truth. We've looked at non-objective truth. We've looked at universal truth. We've looked at non-universal truth. We've realized that when it comes to certainty, science is not as certain in its truth claims as the Enlightenment would have hoped. Today, we're going to be looking at whether or not science seeks and or finds truth. So, if you go back to the beginning of sort of modern science, someone like René Descartes, he was very clear on this topic. His discourse on method, as it's usually called for short, for long was called Discourse on the Method of Rightly Conducting One's Reason and of Seeking Truth in the Sciences. Descartes was in no doubt whatsoever that science was for seeking truth. And even to the present day, we can find people like John Polkinghorne, an eminent scientist at Cambridge University, who said science is concerned with the search for truth. So this seems like a done deal. We can move on from here. Were it not for someone like Neil Gershenfeld at MIT, who says the most common misunderstanding about science is that scientists seek and find the truth. They do not. So here we have a misunderstanding. People, eminent people like John Polkinghorne, think that scientists seek and occasionally find the truth, and Neil Gershenfeld says they do not. So even scientists, between themselves, practicing scientists, can't agree on what they're trying to do. Are they trying to find truth or not? So this is a puzzle, and we're going to engage with it for this lecture. So regardless of what scientists think they're doing, let's ask the question, can science find truth? Can it seek truth? And those two are slightly different questions. I can seek my keys, but not find my keys. So truth seeking and truth finding, two slightly different things. Can science do either of them? And we're going to break this down. We're going to say, first of all, is science competent to find truth? Is it able, in principle, to find it by whatever means? And the second question then is, would science recognize truth if it found it? It has truth in front of it, in its hands. Would it say, yes, I know this is truth? And would it say so with any reliability whatsoever? And I'm going to say that the answer to the first question is maybe. Science might be competent to find truth. And does science recognize the truth if it found it? I'm going to say no. With some reliability, maybe. Better than a coin toss? Open question. Is it guaranteed to find truth? No. And let's illustrate this with an example of phlogiston. Okay, history of science. Does phlogiston exist? So Joseph Priestley in 1770 said, yes, it does. He developed an excellent theory of chemistry, and he was asking questions like, why do some things burn and why do other things not burn? And the answer was, if something has more or less phlogiston, it will be more or less inclined to burn. And so the amount of phlogiston something has tells you how likely it is to burn. Now, Lavoisier, 5 years after Priestley published his work, said, no, it does not exist. He very carefully measured burning reactions. He took air and fuel and burned them, and he weighed what he started with and he weighed what he ended with, and he said, phlogiston, if it exists, is immaterial and massless. Now, a thing which is not made of stuff and a thing which has no mass, I mean, it's as good as it doesn't exist, right? My imaginary friend is immaterial and massless. And we argue, yes, that's a sign that your imaginary friend doesn't exist. So Lavoisier said, I have demonstrated, I've collected everything that was in this jar before, and I've collected everything that's in this jar afterwards, and I have demonstrated that there was no phlogiston. Or at least if there was phlogiston, it's immaterial and massless, so I shall say there is no phlogiston. Now, Gibbs came along a little over 100 years later and said, okay, I have a new concept called Gibbs free energy. This helps us to understand why something burns or why chemical reactions in general take place at all. Now, Gibbs free energy is immaterial and massless, or if you take E equals mc squared into account, it's as massless for the precision that they were able to measure at the time. And notably, the Gibbs free energy of the oxygen per unit mass of reactant that you have in your system will tell you whether something's going to burn or not. Now, phlogiston is a catchier name than Gibbs free energy of the oxygen per unit mass of reactant, but they're telling you the same thing, whether something burns, and they have the same property, namely they're immaterial and they're massless. So Gibbs said, albeit not in this language, yes, it does exist. So now we can ask ourselves the question, is science competent to find the truth? Maybe. I mean, you know, if phlogiston does exist, then Priestley and Gibbs both found that answer. And if phlogiston doesn't exist, then Lavoisier found the answer. So one of them found it. Would science recognize the truth if it saw it? No. If Priestley had the truth, then Lavoisier didn't recognize that because he threw Priestley's answer out. And if Lavoisier had the truth, then Gibbs didn't recognize that because he threw Lavoisier's answer out. So at some point here, someone had the truth and didn't recognize it. Now this causes us a problem. If we take this view of science that says science is remarkably immune to engaging with the truth. If we take someone like Richard Dawkins, that great defender of the truth in science, Dawkins says science gives us the truth. He would agree, strongly agree, in at least this respect, with John Polkinghorne. They agree about a good many, they disagree about a good many other things, but on this respect, they agree. Science gives us the truth. And when asked to justify that, he says, how do we justify that science gives us the truth? It works. If you base a medicine on science, you cure people. If you base the design of planes on science, they fly. If you base the design of rockets on science, they reach the moon. It works. The full quote was slightly longer by at least one word, but I'll let you go and look that up. Now, this is a problem because we either have to say science doesn't work. Richard Dawkins is wrong. Science doesn't work. Planes don't fly. Medicine doesn't cure people. And it takes a very bold philosopher to say planes don't fly. Or we say Richard Dawkins is right. Science does give us the truth and planes do fly. In which case we have to go back and try and work out what was happening with Lavoisier and Priestley. On the other hand, we can say science doesn't give us the truth. Science is not seeking for the truth and science is not finding the truth. And yet planes still fly. And that seems surprising and might need a little bit of digging into. Or we can say there are certain types of truth that science finds and certain types of truth that it doesn't find. And there's one of them going on with Priestley and Lavoisier, and there's a different one going on with building planes. So let's have a look at different kinds of truth. Now, we've already, in previous videos, looked at different kinds of truth. Universal and relative truths or objective and subjective truths. Why do things burn? The Gibbs free energy, that doesn't seem like an objective subjective divide. We can't pin and say, well, me getting on a plane in Hong Kong and landing in Munich is a subjective experience, or my house burning down is a subjective experience. These kinds of truth that we've had before don't seem to solve the problem that we have here. So what we're going to do is we're going to invoke another set of different kinds of truth, namely noumenological and phenomenological. Okay, so for those of you who haven't come across those words before, the noumenon is the thing in itself as it exists, independent of me or my understanding of it or my apprehension of it or my engagement with it. It is the thing out there. The phenomenon is the thing, the appearance of a thing as it appears to me. So, can this distinction help us with solving Dawkins' problem? Now let's consider a phenomenon. If I get into a plane, back in the time when I was allowed to get into planes, and I took off from Hong Kong and I landed in Munich, then this was the thing that appeared to me, right? It was before my eyes. There was a big sign that said Hong Kong, and then there was a plane, and then there was a big sign that said Munich. This appeared to me. This was a phenomenon. But if someone said, by what mechanism did that plane manage to get off the ground, right? I know that rocks fall. That's a phenomenon. I know that planes don't seem to fall out of the sky. That's a phenomenon. But by what mechanism? I know lots of differences between rocks and aeroplanes. What's the important difference between a rock and an aeroplane that makes an aeroplane fly and a rock not? Well, when you're designing an aeroplane, what you do is you say, okay, we have air, which is a fluid which flows over my wing, flows over my wing this way. And that gives me lift, and that allows my plane to fly. Now, no one has ever seen the fluid, which is the air, going over an aeroplane wing. You don't see it on this picture here. It's just not there. You see a wing. No one's ever seen a fluid giving the wing lift. So, on the other hand, someone might say, the air is not an infinitely divisible fluid. It contains lots of atoms, which I can treat like ping pong balls. And as those atoms hit the wing, that is what gives me the lift. Now, this is not the thing which I observe. Now, either of these we then posit as noumena. We posit this as the thing which is going on, distinct from the phenomenon I see, which is the plane is taking off. Now, similarly, one could posit a different noumenon. Someone could say, we have magic, we have pixie dust, which is sprinkled across the wings, and this is what causes the plane to fly. Now, obviously, one can say, you've never seen pixie dust, you've never even seen pixies. To which the response can come, you've never seen atoms bouncing off a wing. Both of them are suggestions about what is actually happening, the noumena, posited noumena, but neither of them are phenomena, things that we have actually seen happening. I am a quantum physicist. I have seen a single atom with my naked eye under very special circumstances. It is possible to see a single atom, but no one has ever seen a single atom going over an airplane wing. So, now looking at this, some people say, okay, the phenomenological truth is our best guess at the noumenological truth. Our scientific theories are an approximation of this noumenological truth, which we have never seen. Our theories are truth-like. They bear some resemblance to the noumenological truth. And so what I'm going to argue now is that science, our scientific theories, these noumena that we posit, are not our best guess at what is actually happening. They are also not approximations of what is actually happening, and they are not even like what is actually happening. The actual thing itself, the thing the universe is doing, is quite distinct from any of our theories about what we think the universe is doing or what we say the universe is doing. So let's have a look at this. Consider a sea of electrons. So all of these are physics examples, solid state physics examples. If you don't like solid state physics, bear with me. Okay, so one views a metal as, here we go, here is a metal. Physicists view this as a crystal of atoms, or a crystal of positively charged nuclei, which are fixed in place. And we have then electrons, which flow around this. Now, we know that these electrons are complicated. We know that they are not point-like particles, they're extended particles. We know that they have their extent follows certain rules. We know that they interact with each other. We know that they have collisions. We know that they have long-range interactions. We know they follow strange statistics. We know that all sorts of weird and crazy stuff is going on. And yet, when we want to model a key, the metal in my key, we just say, I'm just going to have an even background gas of electrons. Now, the crazy thing is, these really simple models are surprisingly good at predicting certain properties of metals. People came up with really, really simple models and said, okay, can I predict the resistance of this? Can I predict the conductivity of this? Can I predict the color of this, the shininess of it? And the answer is yes, you can. And you do the really simple model and people weren't happy with a simple model, so they did this much more complicated model. Whoops, they did this much more complicated model where they took everything into account. And the complicated models gave the right answer, which was good. But they also gave the same answer as the really simple models. And if you're given a choice between, do you want to do lots and lots of calculations to get the right answer, or do you want to do a really simple calculation to get the right answer, you do the really simple calculation because you're not stupid. Which means we have this theory of electrons that we use and is considered a scientific theory, and yet it's not our best guess as what is actually happening. We could argue, of course, that this is at least, if it's not our best guess, it's an approximation of what's really happening. And the important thing to realize about physics is that physics theories, good physics theories, are not even approximations of what is happening. Okay, so let's consider I have a pile of positive charge and I have, along with that, a pile of negative charge, and they're almost paired up perfectly. But over here, I have a negative charge missing. So this here is a hole. Now let's imagine that this electron jumps over into the hole, and then this electron jumps over into the hole. And as that process continues, it looks like this. Now, what is actually happening is there's a pile of electrons jumping across one at a time. None of the electrons have moved more than one space. And they're all moving nice and slowly. And they're all negatively charged, moving this way. Now, on the other hand, let's look at this, taking these together, right? If I look at the average charge of this, the average charge of this is 0, and the average charge of this is positive. So let's start again and just look at the average charge. So here the average charge is positive, and here the average charge is 0. So that's positive and a whole pile of 0. Now the average charge, as each of my electrons hops this way, is actually a single positive charge going that way. Now, if someone gives you a piece of metal in which this situation occurs and says, you can keep track of 1 billion electrons going that way, or you can keep track of one particle going that way, and the maths for one particle going that way is easier, which one are you going to do? And obviously you say, I'm going to do one particle going that way because I like easy maths. Now, you can then, in fact, you can assign an effective mass to this particle. You can assign an effective charge to it. You put an electric field across this and it goes that way, which means you know it has a positive charge. So you now have in your model a particle going this way with a particular mass and a particular charge. And this is not an approximation of anything. You have 1 million particles or 1 billion particles being approximated by 1. These are all positive charges going one way, approximated by these are all negative charges going one way, approximated by a positive charge going the other. This is not an approximation. This is a fiction. And we're okay with that because it gives us the answer we want. Okay, so there's, at least in this previous model, there's something which you know, it looks like there's something truth-like about it, right? There's motion going on, and there's, you know, even if it's not the actual charge, it's like the average charges. So there's something that's at least, you know, bears a resemblance to what is really going on. And that's nice, but of course, science can throw out theories, or can come up with theories, let me say that way, that don't look like what's going on. So let's consider a proposal by Paul Dirac. Now, in this situation here, we have this hole, and we have this net charge, and we can kind of come up with this particle here. Now, he said, let's imagine that we have this is our world here, and this is my particle. But the problem that he faced was this particle wants to seek its lowest energy level. And its lowest energy level is not 0. If this is our 0 energy line, its lowest energy level, he found, was not 0, but in fact down here somewhere there was an infinitely deep hole into which it could fall. So rather than just falling from whatever energy state it had to 0 and stopping, it would, you know, when it did this, it would just emit some energy. But if it falls down an infinitely deep hole, it will emit an infinite amount of energy. And it's a pretty easy observation to see that you can have a particle that doesn't spontaneously emit infinite amounts of energy. So what he said was, he said, right, in all of these energy states down here where my particle would like to fall, I'm going to fill those up. This electron cannot fall there because there's lots and lots of other electrons. How many? Well, it's an infinitely deep hole, so I shall fill it with an infinite number of electrons. Now, the problem he had there was an infinite number of electrons have an infinite charge, and in fact an infinite charge density. So he said, what I also have down this hole is I have an infinite background charge density, which is infinite and positive, to balance out the infinite negative charge density of all of my electrons that I've just shoved there. Now, this seems a little bizarre. Wouldn't it just be easier to say you can't go below 0? But he concocted this because the maths was elegant. And then he said, this leads to a prediction of a measurable observation. And this is the prediction. He said, this electron here can be excited up here. So if I shine in a photon that excites this electron up here, I will get where before I had nothing. I now have an electron here, and I have a space here where an electron isn't. And this space here will be effectively positively charged because of my background infinite charge. And this here will look exactly like an electron, just like this one. It's just this one spontaneously appeared because I just excited out from there. And then after a while, this can fall back into the hole and it will emit a photon. This is a prediction, and people went and looked for it, and they found this background effect. So you've got this crazy, crazy idea of an infinite number of electrons filling an infinitely deep hole, cancelled out by an infinite background charge density. And it leads to a prediction which came true. And you go, well, that's nuts. And he got the Nobel Prize for it. But between writing the original paper and picking up the Nobel Prize, he said, we can rewrite this maths. Here's what we're going to say. This is what he presented in his Nobel lecture 3 years later. He said, we're not allowed to go below 0. We're not just that's silly. Let's exclude this. But here's what I can do. I can bring in my photon, and this photon creates not, you know, this electron here existed before and just was excited here. He said, no, it's not that I excited a pre-existing electron up into this positive energy thing. I'm going to create an electron. But by symmetry, I have to create an anti-electron here. So this previously was a hole. It wasn't a real particle in our previous example with electrons going back and forth. And that positive charge moving across wasn't a real particle. Well, this here isn't a real particle, but now he said, no, this is a real particle, and I'm going to call it an anti-electron. And when these two recombine, they recombine and they emit a photon. Now, these two theories will always give you exactly the same predictions, because mathematically, except for a transformation that's just maths, mathematically, they're exactly the same. There is never a prediction that this theory will make that this theory doesn't make. And there is never a prediction that this theory makes that this theory doesn't make. There is no way experimentally you can tell the difference between them. The reason we pick this one is because it doesn't require us to have an infinite number of electrons sitting around that we can't see. And the reason Dirac picked it is because this one just seems less crazy, though in his Nobel lecture he said for anyone that is uncomfortable with the idea of creating particles and antiparticles, well, it's just like this. So he himself said, if you don't like this idea, think about it this way. They're doing the same thing. Now, given they're both identical, which one of these is actually what the universe is doing? We don't know. And we don't even know how to find out. All of the atoms in your body are made up of these subatomic particles, which might be doing this, or they might be doing this. And we don't know. So to say, well, this has a sort of truth-like nature that this is like, seems to be stretching truth-like rather far. So science is really good at dealing with phenomenological truth. If we want to know what happens as it appears to us, if we want to know when I get in this plane, is it going to take off? Is it going to land in Munich? It's really good at that. If I want to say, when I test the resistivity of my key, what number is going to appear on my voltmeter, then science is really good at that. If I say, when I put a photon into a cloud chamber, what is going to happen? When is my detector going to go ping? Science is really good at that. But if you ask the question, what's happening underneath? What is the universe really doing? Does my detector go ping because I've just created 2 new particles? Or does my detector go ping because one pre-existing particle has been excited into a new energy level, leaving a hole? And science is really bad at answering those questions. We can come up with theories that use models for it, but if we ask, is this what the universe is doing, we genuinely have no idea. So now we can return to Richard Dawkins' claim that we started with this off. It's clearly a question of truth with which he is concerned, but he doesn't tell us explicitly what kind of truth he cares about. So let's have a look. What examples does he use? Medicine. If you base medicine on science, you cure people. This is, you know, a person is coughing, I give them a thing, they stop coughing. These are phenomena. These are things as they appear to me. I'm not asking these deep underlying questions as to what is actually going on. How is the chi flowing? I'm asking things as they appear to me. If you base the design of a plane on science, they fly. Okay? Now, I can have different models of what's going on. I can say I have laminar flow where it's just, you know, a liquid fluid flowing over the airplane wing, or I can say, no, the air is billiard balls bouncing off the airplane wing. I can do these different posited noumena, and I can remain entirely agnostic regarding the actual noumena, and yet the phenomenon of does the plane take off is a phenomenon. If you base the design of rockets on science, they reach the moon. Again, if your rocket explodes on the launch pad, this is as it appears to your senses. Questions of what's actually happening, what the universe is really doing, is quite by the by. So these issues are questions of phenomenology. They are how things appear to us. So science is very good at dealing with phenomena. Science is spectacularly bad at dealing with noumena. And we cannot conflate the two and say science can tell us this, where this is a claim about what the universe is actually doing, rather than how the universe appears to our senses. And we should also be wary that the models we have, however effective they are at making good predictions about how things appear to our senses, telling us when our detector is going to go ping, we should hold them very, very lightly with respect to any conviction that they are telling us anything about what the universe is actually doing underneath. So there we go. We now have another kind of truth to add to our list. So we've previously looked at universal and relative truth, then objective and subjective truth. Now we've looked at noumenological and phenomenological truth. And in the next video, we're going to find another pair because the list is not yet done.